So for example, let's say on average you're on time to class, right? Every day, let's say this class is what, 9:20? So suppose you get here on average at 9:20, but if you look at the data points, if they're centered, then most of the time you're here at 9:19, 9:21, 9:20, 9:18. All that is telling you you're near the center. But if you're here at 9:30 and then another day you're here at 8:50, on average you're here on time, right? But you see what I'm talking about? Because you average those 2 points together, but they're too spread out. So you have a lot of variance. So you're varying too much on your arrival time. Does that make sense? So you're going, same thing, you're going to work, right? You gotta be there by 8, get there at 9, or you get there at 7. On average, you're there at 8, but your boss probably thinks you're a weirdo. So dispersion talks about the spread of your data. How much is it varying? Okay, it becomes important in stuff like manufacturing when you're building things. If you have too many defects, that means that your stuff is varying too much. Yeah, on average, you might make an okay product, but out of if half the things you sell are broken, the other half are okay, then yeah, nobody's gonna like it, right? So that would be an example of your data being too spread out. You want all your, like when you build a cell phone or something, everything needs to be within a certain tolerance. That tolerance shrinks depending on how small the details need to be. Technology requires very tiny tolerances, meaning the data cannot spread too much. So all this comes into play all over the place, okay? In essence, that's what dispersion means. How spread out is your data? But let's talk about a few formulas that we're gonna need. First one is the definition of range. The range R, capital R, of a variable is different from range in math in functions. Is the difference between the largest and the smallest data value. Basically, range is equal to R, which is equal to largest value minus smallest value. So if they ask you to calculate the range, that's all you have to do. Just look at the data set, pick the biggest, subtract the smallest. Nothing else. I don't think we need an example for that. Is that clear? All right. Then the next thing, the important measurement or statistic for measuring variance. The population standard deviation of a variable is the square root of the sum of square deviations. About the mean. divided by the number of observations. Okay, so let me just go ahead and give you the formula. So we use lowercase sigma for standard deviation of a population. Okay, so if you see this lowercase sigma, they're talking about a population standard deviation. So this is equal to your first data point minus mu, your average, squared, plus this next data point minus your average squared, all the way till x capital N. So same notation as last time when we talked about the main formula, right? We said capital N was the total for each total observation in the population. Mu was the mean for population, okay? X capital N minus mu to the capital, well, actually squared, sorry. This should be squared. All over capital N. If we use a sigma notation, it's a little easier to write because that looks funky. So the square root of the sum of xi minus mu squared. But you see how it's very similar to the, oh, well, do you remember the formula for averages, right? You're adding all the data points. So we used this formula last time. X1, X2, all the way to Xn. This is very, very similar. But what we're calculating is actually the average distance from the mean. See how we're taking each line and subtracting it from the mean? We square it, so we have positive distance. We add up all those distances away from the mean. Every single observation, your data, divided by the total. That's basically how far am I away from the average on average. In other words, the measurement of dispersion. Does that make sense? So, well, we just talked about dispersion, right? Spread of your data. This is a good statistic to measure that. Now, the formula for the sample is different. Remember how last time we talked about mean for population and mean for sample? It was the same thing. Here it is not the same thing. So let me give you that formula. I'm going to skip the paragraph because it's very similar definition. It's in the book though, if you want it. So everything's the same except it's for a sample, okay? We use lowercase s for sample standard deviation. So we see if they want a little s, then you should be working with the sample. Formula, we'll use x bar because it's a sample, right? lowercase n is the total observations in a sample, minus x bar, which is the average of a sample. Everything divided by the total, which is lowercase n. Summation formula would be the sum of x sub I minus x bar squared over lowercase n. Now, stack crunch, Excel, your calculators can give you standard deviations. You don't have to crunch this by hand, but it's not too bad, right? I mean, you just take each one, unless you have 1,000 data points, but you have like 4 data points, you just take the first one, minus the average, square it. Again, the second one, minus average, square it, you just add them up. That's all it is. Okay. Any questions on the definitions and formulas? Oh shoot. -1. That's the difference. The difference is you have to divide by n minus 1. Okay. Oop, I think there's one last thing. Oh, wait a sec. Turn the page in a moment. So the first measure of dispersion was range. Second one was standard deviation. Third one is going to be variance. Okay. You guys cool on this page? All right. Just let me know. Slow down. The variance of a variable is the square of the standard deviation. Population variance, we use sigma squared. So if they ask for sigma squared, they're asking for the variance. Sample variance is s squared, lowercase s. Okay. The last thing, I think the last thing I need to mention. The empirical rule. So if a distribution is bell-shaped, well, you can make a lot of assumptions, or I guess a lot of things are true, I should say. So if a distribution is roughly bell-shaped, then number one, approximately 68% of the data will lie lie within one standard deviation. In other words, if you go out one sigma in either direction, if it is bell-shaped, you have 68% of your data or your population. Okay. The majority of people are within, like, whatever we're talking about IQs or heights or whatever. A good chunk of us are within one standard deviation from the center. Center being your mean, standard deviation being the measure of dispersion. Okay. So if you got two standard deviations, then that means you are above average, quite a bit above, or quite a bit below, depending on which direction you go. Right. Number two, approximately 95% of the data will lie within two sigmas. So saying the same thing in a different way, right? Two standard deviations. So most of the time, most people lie within there. The third, going to third, is a very small percentage. You guys ever heard of Six Sigma? No. Comes up in like manufacturing and engineering. When they're building something, they want to be within 6 sigmas. So meaning 99.7%, right, are contained within the data. So I have that much control, meaning my errors are incredibly small. I don't make stuff that's broken. Like if I'm manufacturing things, if everything is within that tolerance, then it's very rare that I sell a defect. Okay. So when they're designing something or checking their parts, we'll have a guy analyzing everything and checking, okay, are we within these parameters, or is there something wrong with one of the machines, or is there something wrong with maybe some worker or something that you start to go inspect if you're out of that range. If you don't care about that stuff, then you probably make garbage. Right? You have to take into account your data and your statistics of whatever you're building. Okay. And if it's really tiny parts, they're not going to fit together if there's too much variance. So 99.7% of the data will lie within 3 standard deviations. Three sigmas on either side. Let me give you a visual in just a second. This is directly from the book. So yeah. I'll put the page back in a moment. The empirical rules that we're writing. Here's the visual. Okay. So like if this is, I don't know, height or something, or weight, most people will be within this range. 68% of the population will be here. Being one centimeter above the mean would be your one sigma above average. Two below, it'd be minus. Over here, you're a little below average. You go out here, 2 sigmas. Now that this people are in the minority, right? It's only 13.5% of the population. So if you're up here, height, you're taller than average, pretty tall. Out here, you're approaching like NBA type height. Okay. That makes sense. Over here, you're approaching very short statues. That makes sense. But the way they're describing it in that paragraph I wrote down, they're saying, well, if we look at them as a whole, 3 sigmas contain 99.7, right? With the tiny chunk outside for the extreme. This is already kind of extreme anyway. 2 was a 95, 97. So you see what they're saying? All right. Let me move that. Okay. Not a very good artist, so I'm not going to draw your bell curve. So I'm just going to show it to you. Let's look at the homework. I think that's everything pretty much. Oh, one last formula. Sorry. Chebyshev's. Some guy's last name. I'm not having a stroke. Chebyshev's. Inequality. I think he's Russian. From like 1800s or something. For any data set or distribution so this is assuming, well, I guess, let's say you have a data spread and you don't know that it's bell-shaped, right? We don't have no idea. This inequality will be true. If it is bell-shaped, then you can make those other assumptions we just talked about, the whole 3 sigma, 2 sigma, whatever. But if you have no idea, or it's not, you can use this. So for any data set or distribution, at least 1 minus 1 over k squared times 100% of the observations lie within k standard deviations. Of the mean. Where k is any mean, sorry, is k is any number greater than 1. You guys know what IE means? It's Latin. It's a id est, meaning that is to say. So that is to say this on the following. At least 1 minus 1 over k squared times 100% of the data. I say the, not that. Lie between mu minus k sigma and mu minus, sorry, mu plus k sigma. For k greater than 1. So if it's not bell shaped, you can only say these, you can make these assumptions. That's why normal distributions are powerful, where you can try to find ways to make it normal. But sometimes real life is not normal. Okay, so basically, try to do a quick example. Because even the sum up is still kind of confusing, right? At least 1 minus 1 over 2 squared times 100% is equal to 75% of all observations. All observations lie within k equal to 2. So basically, if I choose k equal to 2, or if that's given to you, you'll plug it in and calculate 75%. So this tells you that 75% of all observations lie within k equal to 2 standard deviations. So it's the same stuff we talked about earlier. It's just we don't have the normal distribution. Okay, so this is more of a general rule. If I choose 3 sigmas, then we'll calculate how many are within. Okay. Anyway, let's go ahead and look at the homework before we run out of time. You guys cool on that page? Sorry, there's no rush. I'll wait a sec. It might be easier to just do this. Okay. So it'll start off pretty chill. And the work itself is not complicated. The idea behind it is just pretty huge. It's important. Uh, you were given 4 to 5 data points. Dimension sample, or you're going to use that as dimension population, you use the signal. Calculation this time will be different depending what formula you use. If you do StatCrunch or Excel, I don't care which one you do. Personally, I think Excel is better because it's something you can use at work, it's always useful. Doing bills or whatever that. So there's my variable. Going to summary stats on columns. Standard deviation is right here. They ask for a variance or standard deviation. Already forgot. That's for both? Okay. Let's go ahead and highlight both then. So hold control and just click to highlight multiple stuff. Make sure we know what variable we're doing those calculations on and compute. So we have my standard deviation for that column and my variance. Okay. But which one did I choose? Did I choose sample or population? I wasn't paying attention. Let's do it again. Summary stats. Let's see. Doesn't seem to distinguish. Let me look at the result again. Hmm. Standard error. Yeah, it looks like they're doing by default sample, not population. So what we found was the sample types. But now the question is, what if they wanted population? How do I switch over? No, That's sampling. Sample. Well, we only have a few minutes left. So let's just go do it in Excel. For now, I don't have time to research that. Download here. That's stupid. You can just type it in there, so it's only 5 points. So since I'm having technical difficulties, they called it a sample, right? 1711.4. If yours works, go ahead and export it. 1711.4, 712. Once you put it in there, you can just say, you know what, give me sample variance, just so we have a notation. You can organize it however you like, doesn't matter. So when you create a formula, just hit equals, and then type what it's called. So if I do variance, we should have two different types. We should have population and sample. So just pick the one you want. We're doing sample type. Double click it. Now it's waiting for the inputs. So just go up here and highlight them. You can close it off or press enter. So there's my sample population. If I want to do population variance, same thing. Equals variance, look for the one with a P, highlight it, then enter. If you want to do mean, the average equals mean, oh, or average. Yeah, they use average here, that's fine. Highlight it and press enter. So those are all my basic statistics. They should be able to do mode and median. Type equals median. There it is. Double click, highlight your data. Got our median. Mode, I don't think we have one. They'll ask you if you have a single, if you wanted to return a single or multimodal type of question. Try multi and see what happens. Not available. Do you see why there's no mode? Yeah, nothing repeats, right? It's only one of each type. Anyway, I like Excel better, but you can use either one. Doesn't matter. Okay. Let me take roll because I'm running